the total, well, in this case, phi derivative with respect to L, and then we just rearrange the terms. So you get, for example...
You don't need to go into it.
Okay. Okay.
Figure it out.
All right. So at this point, first thing I'm going to do is I'm going to take the partial derivatives of L and Y, and I am going to explicitly write them in L. I'm going to collect all the terms in L because there's a nice simplification that happens. Partial L, partial x prime. Okay, so that brings our top square root down to the bottom, and we get, I'm just going to also flip the R and the G. And so this is RE over G, and let's see. Yeah, that's good for now. I'll just keep that there. And we end up with x prime, and then we have radius of the earth squared minus x prime squared minus y prime squared times x prime squared plus y prime squared. Okay, so this looks like a mess until we make a simplification out of that. Okay, let's try and re-express this back in terms of L. So one way to do that, like the only difference between L here and this derivative here is well, we just is related to this square root here. Okay, in the denominator. So actually, if we multiply the top and the bottom by the square root of x prime squared plus y prime squared, we end up with the result. So I'm just gonna, okay, yeah. We just end up with x prime L is equal to x prime squared plus y prime squared. Right? As a simplification. We get the same thing with the partial with respect to y prime. Well, watch what happens when we plug it into these expressions. Okay, so partial L, partial y prime, same thing, y prime L over x prime squared plus y prime squared. Okay, so let's go ahead and plug this into our first one for Cx. Well, we end up with x prime squared L over x prime squared plus y prime squared minus L. And let's bring it all under the same common denominator. We end up with minus y prime squared L over x prime squared plus y prime squared. Like that. And then for Cy, we get the same thing. We end up with minus x prime squared L over x prime squared plus y prime squared. So these are two constants, right? Two constants of motion. Watch what happens when we add them together. So a constant plus a constant is still a constant, right? We get a nice little statement. Basically, we get that our Lagrangian under this minimization will evaluate to be a constant. Okay? Nice little simplification for when we look back at our T1 and T2. Now at this point, I took as ansatz that we're looking at a hypocycloid solution because explicitly decoupling these is kind of a bear. But what we do end up showing is that yes, once we substitute in the hypocycloid solution, parameterization, the Lagrangian itself does end up being a constant. Okay, so here we suspect this, and now we just show it with the solution. Shall I go through it?
I mean, this is one of those things that if you didn't guess that, you're screwed.
Yeah.
Well, I mean, he told us it's going to be a hypocycloid, so at that point we're just like...
hypocycloid, so if you just show that the hypocycloid is an answer, you're fine. You don't have to guess it out of nowhere.
Yeah. Well, I can show what the Lagrangian will evaluate into. I mean, I could do the steps, but I'll just evaluate it. Yeah, it just ends up being this.
I trust Goldstein, he knows what he's talking about. It's a hypocycloid.
Yeah.
Yeah, well, the Lagrangian, once you, well, I'll just for reference, so put down just what the hypocycloid parameterization is. And I'll leave it as like, exercise for later. For you guys.
Exercise 6A.
Sure. Okay, so,
Kind of thing that you can put in the book is, it can be shown that.
Can
Right.
easily be shown.
Oh. I only took a page.
oh, man, it's there. So this is what the hypocycloid solution. This R is radius of the Earth. This is R cosine R over R minus 1 phi. And then Y phi is equal to R E minus R sine phi minus R sine radius of Earth radius minus 1 phi. So that's just, the hypocycloid solution. And once we substitute these into the Lagrangian, we end up with this. Once the smoke clears. Radius of the Earth over G times radius of the Earth over R, 1. That's a constant. Where this R here is basically related to when Goldstein was talking about the arc length between LA and New York, was it?
Whatever it was.
Yeah. But basically, we can evaluate what that R is at this point from that statement. Okay. So just a bit of the geometry of this hypocycloid. Sorry, pardon, not really all that great, but as so long as it gets the idea across.
Except does it connect for sure, like that?
How do you mean?
Does it connect? Does it repeat after?
Is it
going
periodic?
around in orbit?
Not all
Is it
hypocycloids
periodic?
are.
Well,
It depends on the distance you choose between.
yeah, it does
The
depend
train,
on the
right?
distance. I mean, you could get it such that it's.
In general, it wouldn't be.
You're right.
Unless,
And
so
general-
so
Unless you
basically,
choose specific ratios.
if you chose that, like,
Right.
I'm going to start my train in New York and I want to go a quarter of the way around the world, then I know that the train will end up back in New York.
There's
Yeah.
a term for that. Is it like quasi-periodic or something where but over time it just gets really, really chaotic?
Well, it's not periodic.
Right.
If there's some kind of constraint.
Yeah. But anyway, we have that arc length.
QPOs are different critters.
Yeah. So here we have like an arc length from for example, LA to New York.
Sure frequencies.
4,800.
Okay. But we just say that the arc length is the radius of the Earth times delta feet, because we have that this is constant. And but what this is also equal to is well, if we're just considering the entire motion that it takes to go through the entire motion, this just becomes equal to also 2 pi r, because that's if you start here and then you consider the interior circle, like it's rotating around, it goes through one full rotation from here to here. Is
Yeah.
what this is saying. Okay, so at this point, then we have and then as you said, this was what was it, 4,800 kilometers.
I think so.
So, basically we get then that R in here is 4,800 kilometers divided by 2 pi. Oh, where is that? Well, I guess I just left it in there. Oh, okay.
750. I don't know, just a guess.
Yeah, well, just if anybody wants to evaluate that. But one thing that can be said at this point is for like the depth of the tunnel, the maximum depth of the tunnel, is it's the diameter of the circle. Yeah? So the depth is equal to 2r, and this I did evaluate. This is just, so the radius of the, yeah, this is just the arc length divided by pi now.
So it's just pretty close. Yeah, no, man.
And so this is this depth is approximately equal to 1528 kilometers.
Wait. The depth is twice r, right?
Yeah, twice
the
R.
diameter.
Yeah, did I just forget to write the 2 here? Yeah.
No. Oh, maybe.
Yeah. Yeah, because r is equal to s over 2 pi, but the max depth is, yeah, here to here.
And then you
Right.
plug that r into there, and
Uh-huh. Yeah. Okay, and then that gives us the minimum value. Which, just for reference, right, this was basically just evaluated as being the constant Lagrangian delta phi. We have an expression for delta phi from all this. Yeah.
what you get from there?
Yeah, and well, just explicitly, the expression that we look at is, well, that's the arc length, that's 1 over g, 2 pi over the arc length minus 1 over the radius of the Earth is our expression for the time of travel.
Okay, good.
Bravo.
And here's in one of the solutions on the web, here is the, some pictures of what it looks like for different ratios of A over B.
You can turn on like some old stuff.
A over b.
Well, the ratio,
You mean for different surface lengths?
right, for the, right. And so, as you can see, well, as the ratio gets smaller and smaller, then it just goes farther and farther in, makes all those cute patterns. And these are for these interesting integer ratios where it is closed. But, you know, something interesting, you guys think we're all so smart the last couple of 100 years that we can solve these problems. You know who was writing down these describing this kind of motion? This is Ptolemaic motion. How are those guys in a, whatever it was, a couple hundred BC, able to describe the stellar motions in terms of these hypocycloids on the sky without fancy mathematics? They didn't have algebra. They didn't even have a decent number system.
That's
I can't imagine how it was all done geometrically, but they were able to figure it out and quantify the motions of the stars on the sky with these, in terms of wheels and wheels within wheels. Pretty amazing. In fact, that might be fun to look up. Another opportunity if someone wanted to get for a paper. See how the hell they did it geometrically. You know that Newton's proofs, at least the ones that he published for gravity and so on, as we'll soon be talking about, but they were all geometrical.
He did it geometrically.
1 over r squared, force law, and all that sort of thing. Actually, he had done it secretly using his new calculus, but in order to convince people, since they didn't know what calculus was and didn't much believe in his fancy new stuff, he had to do things geometrically. And I have read through that a long time ago, and quite beautiful and amazing, but I certainly couldn't reproduce it without thinking a lot about it. At any rate, okay, a problem which shows you how nasty these, particularly these brachistochrone kind of problems can be, and how you can use these techniques to use variational principles to get solutions to things that look like they might be nearly intractable. I mean, it is really pretty amazing that you can find the best not just number, but function. That's pretty tricky stuff. Okay, so another one is this number 8. So the Goldschmidt solution, which I misinterpreted when somebody came around to ask me about it.
Well, I got it to work out somehow.
Anybody else get it to work out?
I mean, I'm like, I have to drift out like a few things. If it's cool, I like after class, just like 5 minutes to just add the last.
I don't know if I would want to present. I hit it with a
Oh,
big numerical
that
hammer.
was due today?
Yeah,
Mhm.
yeah.
Oh, okay.
Next time.
Oh, we'll do it next time. We're essentially out of time now. And I wanted to give a wrap about
Yeah.
the Lagrange multipliers, and started reading a little bit on the web about it. And actually, I come back at the end of reading around what's out there. If you look up Lagrange multipliers on Wikipedia, once again, I'm blown away by how much good stuff there is in Wikipedia. People are really putting a lot of work into it. But you will get confused if you look there. Be careful that there's a lot of other use of Lagrange multipliers if you're wanting to poke around a little bit in other areas, many of which are seeking a single solution for a point. So there's this nice geometrical interpretation which you'll see also in the Wolfram site, and making some nice contour plots and showing that you take the gradient of your favorite function and the gradient of this constraint function, which is multiplied by the Lagrange multipliers, which is in fact 0. And what you're really doing is adjusting the gradients so that you're getting the vectors to be parallel with each other. And you're solving for the point where these two functions, the gradient of your Lagrangian and this constraint function, are parallel to each other, but not necessarily the same magnitude, which is a nice way to understand why it's an undetermined multiplier. We don't really care what it is, but it's a number that multiplies this other function. And so that helps understand that a little bit. But the bigger picture with many, when you have many q sub i's and many different constraints, it gets pretty confusing. But a lot of people are using these Lagrange multipliers in various other things. You'll see from economics, with all of the usual wacko assumptions of economics, with a perfectly informed and rational consumer who understands all of these things will make the following decisions of cost-benefit analysis and so on. So you can use Lagrange multipliers to solve for how you should price your product, for example. But you have to know something that is called the Laffer function, which tells you how the response of how much demand there will be as a function of the price, which is obvious when you think about it. Should I produce more at cheaper cost, and what will maximize my profit? If I have some function that predicts that, then I can figure it out. But of course, you never know that. So that's an example of the usage. But also, I think in chemistry, kinetics and so on, and other areas. So it's good to learn something about it, and it is a weird kind of a trick, and always has seemed very strange that you're multiplying, you're putting in something that you know to be 0 into your equations. And so the way it works out from the Lagrange part, you get whatever the number of dimensions, you get, say, 3 dimensions, you get 3 equations from the Lagrangian. If you have 2 constraint functions, then you'll get 2 more equations, which are the equations of that constraint, where it's some constraint g of x and y is equal to 0, or equal to some constant, which you then write as g of x and y minus the constant. Multiply that by the Lagrange multiplier and add it in. But then you still have that constraint equation at the end. So if I have 2 more constraints, I get 2 more equations. So I get, say, 3 plus 2, I have then 5 equations and 5 unknowns. So the game works out. Okay, well, we'll go on with these problems and this is Wednesday, Friday, try to finish up with this chapter and get more, in a way, this is kind of a side tour. Get back to central force problem and on to more straightforward classical mechanics in chapter 3. That means I gotta pick out problems for chapter 3 and all of that.
Chapter 3, maybe 2 weeks.
Yeah, probably.
Sorry.
I mean, I haven't read through it yet, so I'm not sure. But I suspect so. Certainly it could be. So we got all this scattering business and so on in there. And one can spend forever on that. And the 3-body problem. Yeah, so I think we'll probably take the full 2 weeks. And there's lots of problems. I mean, I'm taking the attitude really that in this course you learn by doing. I can stand up here and write down these fancy equations and they'll just blow by you. You really learn something when you sit down and struggle with that Perkistic Home problem, for example. You won't forget that. Right, okay, see you guys on Friday. We don't even have to have Eric bugging us to be out here.
It's nice.